Good morning. Here we are once again at the physics video lecture, Physics 105B video lecture 29. And today we're going to do the free symmetric top and pretty much a redo. Had a sign error last time and we didn't complete the project. Anyway, so I'll more or less take it from the top. So we're talking about the Euler equations, but first let's look at the situation just from the standpoint of a rigid body in the lab frame. So then we know that the time rate of change of the angular momentum is equal to the external torque. And that's very difficult to deal with because we have L is equal to I omega, where this is the inertial tensor. For the record, I'll put it in there again. We're integrating over the body, dm r squared. Trying to put delta there, delta ij xi xj. Okay, so what that means is d dt I omega has all manner of time dependence in this entire expression equals net torque. So what we do instead is transform to the body frame. So next, use dA dt for any vector. Lab frame, body frame gets the prime here. Omega cross A. And when we calculate that, and in fact, what I'll do is I'll go from here straight to the free case and let tau net external torque equals 0. Okay. So that brings us to the Euler equations, the free Euler equations. Which we had up last time. And I'll put them in this form. d omega 1 dt is equal to, and do I get the minus sign there? 2, 3, yeah. Yeah, I'm gonna write them all out. I2 minus I3 over I1, omega 2, omega 3, and cyclic d omega 2 dt is equal to I3 minus I1 over I2 omega 3 omega 1, and the third one, which we'll put here, omega 3 dt I1 minus I2 over I3 omega 1 omega 2. Okay, so those are the Euler equations when the torque, the net torque is equal to 0. So yeah, we just transform this side. And now omega 1, 2, and 3 are the components of the angular velocity vector with respect to the body frame. So the next thing I'm going to do is go ahead and draw the body that we're talking about. And this time, to be concrete, we'll use a disc-shaped object. And, okay, so, because we're going to do the symmetrical top. So the example is the symmetrical top. And a disk is a good example of that. So say we have a body frame or some kind of flat disk there. X1, X2, X3. We know that, okay, symmetrical top, so we have I1 equals I2. I1 is not equal to I3. And for a flat disk, flat uniform disk, we know, okay, so for a flat uniform disk, we know that the Z moment of inertia is twice the X and Y moments of inertia. So we have I1 equals I2 equals a quarter mr squared. I3 is the one we're used to, 1/2 mr squared. So even if it's not a perfectly flat disk, as long as it's flat enough, we know that I3 will be greater than I1 and I2. We're going to make use of that just to have a good concrete example. So we consider the case where I3 is greater than I1. And now we have something like an inertial tensor. We'll say I1, 0, 0, 0, I1, 0, because I1 equals I2 and 0, 0, I3. And we know that that one's bigger. Okay, so what does that give us for our Euler equation? It's nothing different than we had last time. So now d omega 3, now I'll just write Euler equations. So d omega 3 dt is equal to 0 because I1 is equal to I2. So omega 3 is constant. So that's the first thing we have. And when we go back into these equations with omega 3 being constant, I'll do it in 2 steps. So now we have d omega 1 dt equals, so I'm going to go ahead and pull a minus sign out, I3 minus I1 over I1 omega 3 omega 2 and d omega 2 dt I3 minus I1 over I2, but again I2 is equal to I1. That's the substitution I'm making here. Got the omega 3 omega 1. And I'm going to even give this a name now. So now I called it lowercase omega last time. That was enough to drive you to distraction. So let's call this uppercase omega. Uppercase omega is going to be equal to this I3 minus I1 over I1 times the omega 3. These are all constants. And we'll keep working on that picture. But then we can write these equations in a simpler form, and the definitions are all here. Okay, let's see. We have, so that d omega 1 is equal to minus capital omega 2 d omega 2 dt is equal to omega 1. And from these two, I have d squared omega 1 dt squared, so 1, is equal to minus omega d omega 2 dt, which is the right side of this, so that gives me another omega and omega 1. And then we just recognize this second order differential equation with the negative coefficient as giving us omega 1 is equal to a cosine omega t. Okay. And I could add an arbitrary, I could add a phase, but let's just go ahead and leave it this way because it's not going to matter what the initial condition is. Okay. So a cos omega t, and then omega 2 is a sine omega t. Had it, then I erased it last time, kept the minus sign in front of it, but d omega 2 dt is equal to omega 1. So if you differentiate this, get the omega out, you've got a cosine omega t, which is omega 1. So that is the solution. And the minus sign, by the way, is crucial here because it changes things. So these are, and then omega 3 is equal to omega 3 is a constant. So those are the three components of the angular velocity vector in the body frame. And so we're going to start drawing it in the body frame and thinking about it a bit. Yeah, that says constant right there. Okay, omega 3 constant. Yeah, and these two components, which are, since they're the 1, 2 components, they are the projection onto that x1, x2 plane. They are moving in time. So this is what we have to look at next. I think we have enough up here on the board to draw some pictures. Okay, we want to collect everything. So this is omega 1, omega 2, omega 3. Yeah, let's go ahead and draw a picture. I want to talk about the angular momentum as well. Okay. Yeah. Let's do the angular momentum first. So, what about the angular momentum? They're both living in that picture up there. We're going to draw them in a moment. So what about the angular momentum? Well, L is equal to I omega. And since we've found omega, let's make sure we do it, or we're clear on this. So we have I1, 0, 0, 0, I1, 0, 0, 0, I3, and then this omega vector is the one we have right here, a cos omega t, a sine omega t, omega 3, this one being a constant. So L equals, okay, let's go ahead and write it as a vector, and then we'll compare the two. So here we have I1a cos omega t, I1a sine omega t, and then I3 omega 3. Okay, I'm going to go ahead and outline these. I have the angular momentum vector. I have the angular velocity vector. Maybe I'm gonna write it one more time. What the heck? Because in your notes, you can space this out, and you've got L and you've got omega equal to just what I have up there, A cos omega t, sine omega t, and then just omega 3. So these vectors, of course, have different dimensions and slightly different direction, but they also share something. I'm going to make a picture now, so I've got this. So what I can do now, I'm going to erase all of this and do a new picture, and we'll be able to refer to what we have up here. I'd say we have everything we need. Yeah, this is going to go. Yeah, everything is up there. Okay, we're just going to reproduce that picture, maybe a little larger. This is the crucial one. Okay, so we have that disk shaped object right here. These are the 1, 2, and 3 x3 axes. And I'll remind you, I showed you a rotating disc the other day, and it was a free top. It was a little different because it wasn't a single one, it was counterbalanced. But nonetheless, the point is that you didn't see this fixed disc, you saw that disc waving around or moving around in space. So right now though, we're in the body frame of that disc, and what's moving are L and omega. And I have L and omega drawn here, and these two components of omega are important. I'm going to go ahead and draw omega as a red vector. So omega has, let's see, okay, 45-degree angle is a bad choice, but we're going to run with it. So omega, I'll go dotted in this direction, like that. So if this is the vector omega, I'll even write omega there. Then it has an omega 3 component, and it has this A cos omega t, A sine uppercase omega t. So that is this projection here. A cos omega t, A sine omega t. And since that projection is going around counterclockwise, or in the x1, x2 plane, we can do a top view of this, but I think you see if that's the x-axis, that's the y-axis, then it's going around counterclockwise. So the point is that this omega vector is doing this. It's describing this cone here as it goes around. This is just a snapshot in time. Okay. And again, the projection A cos omega t, A sine omega. By the way, this letter A is not an amplitude per se. It itself has the dimensions of a frequency. Okay, remember the cosine is dimensionless, has dimensions of a frequency. And the entire vector, it has 3 components. Those are those 2. The third one is fixed, and therefore it sweeps this cone around. Now, what about the angular momentum? You'll notice that the angular momentum has a projection onto the x1, x2 plane that is parallel to this projection. Okay, it's just multiplied by I sub 1, and it has a third component that's just multiplied by I sub 3. Now, since I sub 1 is not equal to I sub 3, these two vectors are not parallel. But because they share the same projection space, they are coplanar. So what that means is that, I'll draw this I sub 3 here, good luck. I'll draw the L, And also because since I sub 3 is greater than I sub 1, this L will be inside here. We had something similar when we had that rotating disk. So this is L, okay? Because it's sharing the direction of this projection. You know, L would be parallel to omega if I sub 3 were to equal I sub 1. Since it's not, the I sub 3 component is proportionately larger. Okay. So because of this construction here, and I'm even going to put an angle theta between L and x sub 3, this is the very important note. X3 hat, which is of course a vector, L and omega are coplanar. Okay, they're in a plane. And again, it's because of the projection onto the XY plane of L being parallel to those two vectors. Okay. Okay, so what does that mean? Have we arrived? No, now we got to do some analysis and make sure I didn't miss anything. Okay, so now we have to just point and discuss. Most things or many things are on the board. Now remember, in the lab frame we have conservation of angular momentum. So in the lab frame, this vector L would be fixed and this disk is wobbling around, okay? But in the body frame where we are now, X3 is fixed and both omega and L have this cone, you know, describe the tip of these vectors. Each vector describes a cone. So I'll do the same thing for this one, except let's scale them properly. I'm going to redraw these cones if I can. Let's see here. Okay, so there's omega. And if I go this far on that side, my other omega vector. Okay, so that's a better omega cone. And then obviously the L one has to be smaller. So tip L over there, we're about there. Okay. So we've still got the angle there. L, X3 hat. Color's not bad, huh? Okay, X3 hat is in that direction. Good, so in the lab frame, both of these vectors, and remember they've always remained in a plane, they're both sweeping these cones out about the X3. I'm sorry, in the body frame, they're doing that. In the lab frame, we would say omega and X3 hat are sweeping cones around L, okay? But since we've calculated everything, we should be able to make the transformation from one frame to the other, or do that analysis. Okay. So there is a frequency associated with these vectors sweeping around X3 hat. And that frequency is this capital omega, which I'll write down again. So we have this capital omega was I3 minus I1 over I1 times omega 3. So in the lab frame, I'm sorry, in the body frame, this is the angular frequency with which these vectors sweep out those cones. Okay. And what we want to do is analyze this and figure out what's the frequency with which these red and blue vectors are sweeping around L, okay, because in the lab frame, that's what's happening. The lab frame, L is fixed and this thing's wobbling and these vectors are going around. Well, the vector that we're interested in, the reason I drew this angle theta here is because this x3 hat, being the x3 of that lab frame, is it's a real fixed thing in either frame of reference, and that is to say you could take your disk and glue on those axes, and then you'd be asking what's the frequency with which this x3 axis is whipping around that point in space. Okay, so I have that axis right, that angle between L and x3 for that reason. So let's put some of this as notes so we don't forget it. In the body frame, L and omega, move around x3 hat, okay, are in motion around x3 hat, which is just the body axis. But in the lab frame, L is constant because we have conservation of angular momentum. And in that case, x3 hat and omega move around L. Good. And this one you don't physically see. This blue one you can at least imagine seeing. We're gluing something on so that you could literally see it. Okay. And so yeah, really this x3, the motion of this x3 hat around L is what we're interested in. So let's see. It's actually enough to analyze this thing, making sure everything is up there. I may do one more picture. So yeah, we had everything up there last time, with the exception, of course, the wrong sign. But this takes a little bit of discussion. Omega, we already know the parallel coplanar. Yeah, I'm going to erase all of this. And I may try another picture. Okay, so we're going to call this precession frequency. We'll call it omega sub precession, like that. So that's the last thing we have to tease out on this discussion. We saw the wobble, so we saw the thing wobbling around, that cone shape. We actually saw that in our demo last time. But we want to get the frequency of that wobble. And we have two different types of vectors here. We have an angular frequency vector. We have a different vector with a different dimension. So we want to reduce it all to frequencies. So we'll start with this omega. We know that omega is the frequency, capital Omega is the frequency with which this projection moves around in a circle. So that's actually the frequency with which these things are going around x3. Okay. So we know the meaning of capital Omega, and what I'm going to do is expand it out, so I have I3 over I1 omega 3, and then I1 over I1 omega 3, so minus omega 3. Now there are a couple of different ways I can write this. This I3 omega 3 can also be written as L sub 3. Okay. I3 omega 3 is L sub 0, so I have L sub 3 over I sub 1. And I introduced that angle theta. You know, we're going to stick with that graph up there. So minus omega 3. So I can also write that as, I'll go ahead and write this here. So this omega can be written as L cos theta, right? L sub 3, that's the projection onto the 3 axis. So it can be L cos theta over I sub 1 minus omega sub 3. So I'm going to hold on to this. So now we have frequency, and this is also a frequency. L over I sub 1 is a frequency, right? And cosine theta is dimensionless. So those are 3 frequencies. And here's the time for our second picture. Or in fact, let's go up here. I'm going to write omega plus omega 3 is equal to L cos theta over I sub 1. Okay, so that's equivalent. That's equivalent right here, okay? L cos theta over I sub 1. Okay, now I'm going to repeat this graph, but this precession frequency that we're looking for is going to be parallel to L. Okay. This is the wobble, or whatever you want to call it, frequency. So we're going to note, and the reason it is because that's what this wobble was wobbling around, as you guys saw it the other day, right? You saw the gyroscope going like this, okay, and that's the frequency I'm talking about. So you didn't actually see L physically, but it was the center of that cone-shaped movement that we demonstrated. Okay. Omega precession, the vector is along the L, along the angular momentum. Okay. So if I do another drawing like this, I'm just going to indicate the disk like this, okay, and we'll take our x3 hat axis there, geometrically this should work out. So these are all now omega vectors. So x3, this is x1 or x2, doesn't matter, okay, one of the two. So let's see, we'll go omega. And then there's our omega 3. And then, so this is the omega 3. This is the omega 3. And this is the omega. again, this capital omega, right, that's the way this projection goes around the x1, x2 plane. It represents a vector that, of course, is perpendicular to that. So the omega vector would be this one right here. And this is going to end up at omega precession, which is along the L vector. So we have this angle theta, as stated before here. And what we can see is, from this construction, omega precession cosine of theta is equal to omega 3 plus capital omega. Well, this, okay. What that means is that omega precession frequency we're looking for is just L divided by I1. Okay. So yeah, you gotta hold on to all these three and ponder them and ponder the geometry, and it all makes complete sense. Okay. Of course, everything that should be on the board is never there. But the fact, the reason I can draw this omega parallel to the axis is because the projection of this blue vector omega onto the x1, x2 at x1, x2 plane, and the projection of this omega vector, which is just the two components with the a cosine omega t. When you divide by I sub 1, you divide L by I sub 1, they have the same length. Those projections have the same length. So this is the perfect geometry. Okay. And so we can finally conclude that the precession frequency that we're looking for, you guys make it neater than I did, but omega precession is L over I sub 1. Okay, didn't leave out a step. Okay, there's a nice application I'll fill in here, and that'll wrap this topic up. Let's see how we're doing. Yeah, this will be perfect. Okay, so just make it even more orderly in your notes. There's an interesting application. You guys can actually test this. Anyway, yeah, so these are all equivalent, right? But we just discovered what this precession frequency is. L over I sub 1, but yeah. Good enough. It's okay, I'm gonna erase this. So here's an interesting example. You can observe this under circumstances. Suppose we have, consider the flat disk. Consider the disk where I sub 1 is what I had written down originally. I sub 1 is a quarter mr squared. I sub 3 is a half mr squared. And now we'll look at this omega precession. Omega precession cosine of theta is equal to omega 3 plus omega 3 plus, and remember what that omega was. It is I sub 3 minus I sub 1 over I sub 1 times omega 3. And I sub 3 minus I sub 1 is equal to I sub 1 divided by I sub 1. So that's just 1. So equals omega 3 plus omega 3. So we get omega precession cosine of theta is equal to 2 times omega 3. So in the limit, where cosine of theta, where theta is very small, cosine of theta is close to 1, you get this omega precession being twice the rotational frequency itself. Okay. And that is visible as a certain kind of wobble. You may see it sometimes if you have a really flat plate and you kind of tip it on the side and let it come to rest on a table. It'll wobble around. And if you pay close attention, you can see that the precession frequency with which this x3 axis would be rotating around is twice the speed with which the plate is itself rotating. Okay. So it's an interesting effect. You can actually find this, play around with it. Okay. I think we are pretty complete at this point. And yeah, this picture you can only try to make better, but it essentially contains everything. The second picture, though, was all just angular velocities, and the fact that this vector and this one are parallel is key to the whole discussion. But it's true, they are. Good, so let's leave it at that and see you guys next time.